Good evening, everyone, and welcome to the Amateur Radio General Class, session number 6. During our previous class, we had a look at the question pool, went through some of the questions that matched the theory from the class, the previous class. We looked at inductors in series. We looked at a worked example for inductors in series. We looked at inductors in parallel. Then we did a worked example for inductors in parallel. We considered the units of capacitance, and then we did a worked example involving units of capacitance. We looked at capacitors in parallel, and we also did worked examples of capacitors in parallel and series. We also did worked examples. So in terms of our curriculum, we have completed the first section, although today we have a couple of outstanding questions to quickly review. We did all of the theory, so we'll just go through the questions very quickly. But we are today going on to our second module, which is circuit components. Again, encouraging everyone to continue your hand at the practice exams. We had a couple of questions from the last class, so let's deal with them. The first one, when we have two different units, example, picofarads and nanofarads, in finding the end result, do we convert to the upper unit or to the lower unit, unless specified in the question? So the answer is, if the question does not specify, you can basically choose which unit you want to work in or answer. That is based on convenience, convention, or what is practical. However, whatever you choose to do, if it's not specified, ensure that you do not lose any precision during conversions while you are actually performing the calculations. It may be more convenient to go with the higher unit. For example, instead of saying I have 1,000 cents, I would probably prefer to say I have $10. All right. So again, convention could dictate which one you go with. You can truncate the final answer, but not before during your calculation. So try to keep the precision during your calculation, and then you can truncate if necessary at the end when you're giving your final answer. Now, the second question is related to the first, and it goes a little further. The question is, why not convert nanofarad to picofarad? Would that be wrong? Because in the question that we were doing, the example that we did, we actually converted from picofarad to nanofarad. So these two questions are actually excellent questions that were asked by the participants. So there's nothing wrong with converting from nanofarad, the units that were given in nanofarad, to picofarad and then calculating. In other words, doing so would have been equally valid. However, the question, and in the case of multiple choice, the available answers will often indicate which unit you may wish to work within. So in multiple choice, one of the answer would be so-and-so, either nanofarad or picofarad, and that will be a clue as to the unit that you may want to work in. But no harm in you working with either, as long as you arrive at the correct answer. Some of it will be a little easier, less digits, in some cases more digits, you know, so it's what you're comfortable with. So very good questions from the last class. So we will now proceed to do a question pool review of the questions that dealt with the theory from our last session. All right. So the first question is, which of the following components should be added to an inductor to increase inductance? So we learned, of course, that when you add inductors in series, that is how you will increase inductance. So that is the answer to that question, an inductor in series. Next question in the question pool. What is the inductance of a 20 millihenry inductor connected in series with a 50 millihenry inductor? So again, dissecting that question, they're giving you two inductors, the values. They're telling you one is 20 millihenry, the other is 50 millihenry. And they're saying, what is the overall inductance when you have them connected in series? And as we learned in the last class, We simply add them up like that, and we end up with 70 millihenries. So again, all of these were done as worked examples in the last session. So if you want details or missed the class, just have a review of the last one, and we go into step-by-step details. Next question. What is the inductance of 3 10 millihenry inductors connected in parallel? So again, we did this as a worked example, but we'll still dissect the question. So again, we're dealing with inductance, and they're telling us that we have 3 inductors, but each of them are 10 millihenry value. And how are they connected? Is it series? No, they told us parallel. So we use the appropriate formula, and we end up with 3.3 millihenries as the answer. Again, worked example in the last class. Next question, dealing with capacitors. Which of the following components should be added to a capacitor to increase the capacitance? So let's dissect that question. So we are dealing with capacitance, not resistance, not inductance, so it's capacitance. And they're saying if we want to increase capacitance, what should we do? How should we add capacitors? Should we do it in parallel or series? But as we learned in the last class, the theory says when you want to increase capacitance, you have to put the capacitors in parallel, and that's how you get an overall increase in capacitance. Next question in the question pool. What is the capacitance of a 20 microfarad capacitor connected in series with a 50 microfarad capacitor? Again, a worked example, but let's take a moment to dissect. Again, they're asking us about capacitance, and we are given the values of 2 of the capacitors, 20 microfarad and 50 microfarad. And how are they connected? Is it parallel? No, it's in series. So we therefore have to use the formula for series connected capacitors. And when we use our formula, trusty formula, we get the answer 14.3 microfarad. Again, another full worked example in the last class. Next question. What is the capacitance of 3 100 microfarad capacitors connected in series? Again, we did this last class, worked example full. But let's dissect it. What are they asking us? Resistance, inductance? No, they're asking us about capacitance. All right, how many capacitors are there in the question? 3 of them. And what's the value of each capacitor? Well, they're equal, and they are 100 microfarad each. But how are they connected? Is it parallel? Is it series? They tell us it's series. So we know we have to use the series formula for capacitance. And what are the values? 100 microfarad each. When we plug them into our trusty formula, we get 33.3 microfarads. Of course, in the question pool, you will see other distractors. They'll tell you 3.3, they will tell you 300, and so on as distractors. But we know when you have capacitors in series, we have to use our trusty formula, a version of this on the screen. Yeah? Okay, moving right along. What is the value in nanofarads of a 22,000 picofarad capacitor? So we did this also as a worked example. Let's dissect it. What are they asking us to do? They're basically asking us to convert from picofarad to nanofarad. That is what they're asking us to do. We have a 22,000 picofarad capacitor. They want to know in nanofarads how much it is. And last class, we learned we divide by 1,000, and that's how we get the answer, 22. Again, fully worked example in the last class. Similar question. Next one. What is the value in microfarads of a 4,700 nanofarad capacitor? Again, this is another conversion. We are converting from nanofarad to microfarad. And as we learned last class, we divide by 1,000 to convert up. So therefore, the answer was 4.7 microfarads. Next question in the question pool. What is the equivalent capacitance of 2 5.0 nanofarad capacitors and 1 750 picofarad capacitor connected in parallel? So let's take our time and dissect this question a little bit. We actually did this as a full example, worked example in the last class. So again, we are still dealing with capacitance, not inductance, not resistance. We are dealing with capacitance. So we know we have to use a capacitance formula. How many capacitors are they? Do they have in this question? So it's a little bit tricky, right? I think I got stumbled during the worked example last class. But let's take it a moment. They're telling us we have 2 5 nanofarad capacitors. So it's actually 2 of them that are valued at 5. Not one of them, two of them at 5. So we already have 2 capacitors, but they're also telling us we have one of 750 picofarad. Notice they said picofarad and not nanofarad. So they're trying to tie us up here, right? They're giving us mixed units. They tell us nanofarad here, but they're telling us picofarad here. So that is why we know we have to do some conversion to work the answer. So how many capacitors do we have? We have 3 of them. 2 of them are 5.0 nanofarad and 1 of them 750 picofarad. How are they connected? Series or parallel? Well, they tell us in the question it's parallel. So we know we need a formula for parallel connected capacitors. And we have 3 of them. We apply our trusty formula. Of course, because they are parallel, we can add them together. But we can't just add them together. We have to convert to a common unit. So we either convert all to nanofarad or we convert all to picofarad. Of course, because the answer in the question was nanofarad, we just chose the one that was given in picofarad to convert to nanofarads. And we simply add them 5 plus 5 plus 0.75, and we got the answer 10.75. Again, fully worked example last class in the slides and also the recording if you need to review. Okay, so we move right along. Next question in the question pool. All right. What causes a voltage to appear across the secondary winding of a transformer when the AC voltage source is connected across its primary winding? So let's dissect this question a bit. So we went into this theory in some detail. So let's dissect the question. What are they asking us? They're asking what. So that means there's a phenomenon. What causes a voltage to appear across the secondary winding? So what are we dealing with? We are dealing with a transformer. And remember, transformer has primary and secondary windings. All right? And how does a transformer work? So they're asking what causes the voltage to appear across the secondary when you apply an AC voltage across to the primary. So remember the diagram that we had with the transformer. We have the primary winding. We apply an AC voltage. And then a voltage appears across the secondary through a phenomenon known as mutual inductance. So remember we did that last class? So that is the answer as to what causes the voltage to appear on the secondary when you apply a voltage to the primary. Mutual inductance occurs, and therefore the lines of magnetic flux cuts across the secondary winding, induces a voltage, and that is what you have on your secondary side through mutual inductance. Okay, we stick into transformer related questions. Next question in the question pool. What is the RMS voltage across a 500 turn secondary winding on a transformer if the 2200 turn primary is connected to 120 volts AC? All right, long-winded question. But let's dissect it. What are they asking us? They're asking us what is the RMS voltage. Now they're just telling you RMS voltage to tie you up there. We just know that when they say RMS voltage, it's an alternating current that's present. So an AC voltage really, they could have asked us that as well. What is the AC voltage, right? But they're correct to say RMS voltage. What is that voltage across a 500 turn secondary winding? So it's a transformer. So we know that the secondary winding is 500 turns, but they will tell us also the primary has 2,250 turns in the primary. That's how transformers work. You have windings in the primary, you have windings in the secondary, and there's a ratio to how many windings in the primary to the secondary. And that is what will give you, given the input voltage, what the output voltage is. So they tell you that your primary or your input voltage is 120 volts. And they're asking you what is the output voltage across the secondary. So you use the turns ratio and you calculate it, multiplying the turns ratio, which is given by the number of turns, 500 over 2,250, and then that turns ratio you multiply it by the input voltage, 120 volts, to get the output voltage of, what is it, 26.7 volts. Again, a fully worked example last class. Let's move right along. Next question in the question pool. What happens if a signal is applied to the secondary winding of a 4-to-1 voltage step-down transformer instead of the primary winding? All right. So here's the question. The signal, right, But let's think of it as an AC voltage, right? Alternating current. They say signal to try to tie you up a little bit, but think about it as an AC voltage, all right? What happens when you apply that voltage to the secondary winding of a 4-to-1? Well, if you apply it to the secondary voltage, the multiplier or the turns ratio, they give you the ratio. They say it's 4-to-1. You don't have to work it out like the previous question where they tell you the number of turns in the primary and the number of turns in the secondary. They don't tell you the number of turns. They just tell you already what your turns ratio is. You know it's 4-to-1. So therefore, the answer is you multiply the voltage by 4 to get the output voltage. Again, we worked this question a bit in the question session last class. Next question. What is the conductor, say again, why is the conductor of the primary winding of many voltage step-up transformers larger in diameter than the conductor of the secondary winding? So let's take this question a little bit slowly. Let's dissect it. What are they asking us? They're asking us about the conductor. That's the wire itself that comprises the transformer. And what are they asking us about the conductor, that wire? They're asking us about the diameter. And they're asking us, why is it in the step-up voltage transformer, why is it larger for the primary than the secondary for a step-up voltage? So if you are stepping up the voltage, as we learned in the technician class, you have to reduce the current. So therefore, in the secondary, the current is lower. If the current is lower in the secondary, remember, the current has to pass through the wire. So therefore, if you have a higher current in the primary than the secondary, then it stands to reason that the diameter or the thickness of the wire in the primary will have to be thicker because the current is higher in the primary. So again, the answer is the reason it is larger in diameter is to accommodate the higher current flow in the primary. Next question in the question pool to round off. What is the turns ratio of a transformer used to match an audio amplifier using 600 ohm output impedance to a speaker having 4 ohm impedance? So we worked this as an example in the last session. We did a diagram and we showed that transformers could also be used to transform audio or impedances, right? So let us dissect the question. What are they asking us? They are asking us for the turns ratio. And remember, transformers, you have a primary and a secondary. Number of windings in the primary and number of windings in the secondary. And if you have a 4-to-1 ratio, maybe you have 4 turns in the primary, 1 turn in the secondary. That's a 4-to-1 ratio. Or maybe you have a 1-to-4. Maybe 1 turn in the primary and 4 turns in the secondary. All right, so that's a 1-to-4 ratio. So that is what they're asking us. But remember, we also showed that because we are dealing with impedances, we have to use the square of the value. And when we use the square of the value in our calculation, our formula ends up with square root. So last class, we presented that formula. And therefore, what we showed was that the turns ratio is equal to the square root of the output impedance over the input impedance. So let's see if they gave us those values in the question. So we have to apply this formula for impedances. And let's see if they gave us the values to work with. So what are they asking us? They're asking us for turns ratio. So therefore, turns ratio is equal to something. What is that something? The square root of the output impedance divided by the input impedance. Did they give us those things? Let's check. Okay, they say having 600 ohm output impedance. So there we go. We have the output impedance to put into our trusty formula here. Did they give us the input impedance? Let's see for the input impedance. There we go. We have a speaker having 4 ohms impedance. So therefore, we have the two values that we are looking at. We have 4 ohms and we have 600 ohms. So the value of the output impedance of the amplifier is 600 ohms, but the speaker has an input impedance of 4 ohms, and therefore we have to match them. And these are the values that we put into our trusty formula to come up with what is the turns ratio of that arrangement. So when we divide and take the square root, we get 12.2. Again, we did this as a fully worked example in our last session. All right, so let us do some theory for this class. We'll take a break in a couple of minutes, about the next 10 minutes or so. So let's press on with some theory. So I trust by now that most, if not all, of our participants have in fact gone through the technician class material, or at least well on your way to reviewing the technician class videos. Because some of the material that we deal with at the general class builds on the knowledge of the technician class. So we'll be touching likely and reviewing some of it, but really you would be at a great advantage if you review the technician class material. A lot of things will be a lot clearer if you were to do so. So review sessions 4 and 5 of the technician class if any of what we're about to present to you there's any doubts about it. So sessions 4 and 5 covers some of this material at the basic level. Okay, resistors. Resistors should not present a challenge to us. We did it in the technician class, so we know the resistor will oppose the flow of current, and we know what the symbol is for resistor. And we said there are different types of resistors. So you have a screen there that shows the different types of resistors, composite resistors, variable resistors, all sorts of other resistors, wire-wound resistors. This shows a little variety of resistors. There are many types. Just like you have a plant like a cherry. Around the world, there are different types of cherries. Well, the same thing with resistors. You have different types of resistors. But we are doing a radio course, and we need to know something about resistors that we have to be a bit mindful of. So remember I showed previous slide that we have something called a wire-wound resistor. We mentioned it, but we're going to go a little bit more detail into the wire-wound resistor and why we need to be mindful about whether we are using wire-wound resistors in our radio circuits. The reason is that a wire-wound resistor consists of a coil of wire that, it is very precise when you create a resistor. This is a construction of what a wire-wound resistor looks like. If you look inside, you'll see a coil of wire. And because it's a long coil of wire, there's resistance or opposition to the flow of current in it. So that's what creates the resistance. And because it's a high precision type construction, you can get pretty precise resistor values. But there's a problem with using wire-wound resistors in radio circuits. What is that problem? Do you notice any similarity to this construction of a wire-wound resistor to another type of component that we did before? If you guessed, hey, wait a minute, that coil looks like an inductor, you would be correct. So it's a resistor, yes, but it consists of wire in a coil fashion. So not only does this wire-wound resistor construction have resistance, but it also has inductance. And you may not want to introduce inductance into your circuit because that could cause issues for you. You may want inductance, but if it's stray inductance or inadvertent inductance, you may not want it. So we have to be mindful when we are using resistors that we choose the correct type and we do not introduce a component that has values that we did not want. So we say that the wire-wound resistor is very high precision, but it may not be a good choice for radio frequency circuits because they are comprised of a coil of wire. And because of that coil of wire, it will present an inductance and affect the performance. So when you're building a circuit, don't just use any resistor. Make sure that you know what you're using. And if you don't want to have that effect, just simply avoid a wire-wound resistor and use another type of resistor that does not have this property. Okay. We next come to capacitors. Again, we should not be any strangers to capacitor. Remember, we said the capacitor in a water circuit is like the tank, the pressure tank. It stores a charge. It holds water pressure. Well, it's the same thing. It holds current. It basically stores a charge for you. And there are many types of capacitors. Again, just like there are many types of mangoes, cherries, and so on, There are different types of capacitors, how they're constructed. They're all capacitors, but you have the electrolytic types, you have the ceramic types, and all sorts of other types. So this is just for FYI, for your information. There are many types. Of course, in our class, we will be focusing on very specific ones. But just to let you know, there are many, many different types of capacitors. And a capacitor is constructed this way. So you usually have two leads on the capacitor, and each lead will go to a plate, a piece of metal. All right, so you have the metal on one side and you have the metal plate on one side, the other side, and they're separated by a certain distance. And sandwiched between them is a material that's called a dielectric. So it's kind of like, you know, you wake up in the morning and you're feeling a little peckish and you want some breakfast, but you decide, you know what, you're in a hurry, you're going to make a sandwich. So you have a slice of bread on the outside, another slice of bread on the inside, and you probably put some peanut butter and jelly, or maybe some butter, or whatever your favorite spread is, maybe a cheese spread, or, you know, maybe a vegetable spread, whatever your fancy. So this is like a sandwich. So that is how a capacitor is constructed, just like a sandwich. And you have two leads going to each side of the plate. So that is how you construct a capacitor, basically. Sometimes you wrap it up afterwards, but this is the basic construct of a capacitor. All right, so there are two types of capacitors that we need to be aware of and talk about for our purposes in amateur radio. We have the ceramic type of capacitor, and if you look at it on our screen here, it looks pretty unassuming. It's very basic. This is the symbol when we are putting a ceramic capacitor into a circuit. Notice how it looks. If you think about it, it kind of looks like how it's constructed. You have the two plates and you have a dielectric in the middle. So, you know, very similar. But we need to be aware that the ceramic capacitor is very popular, used quite a bit in electronic circuits because it's low in cost, very cheap to produce, and we use it regularly. However, the thing about ceramic capacitors, you cannot get high capacity ceramic capacitors. You get very low value capacitors. So just bear that in mind. You cannot use it where you need a high capacitance. For example, if you're filtering an AC power supply, you cannot use it there. This is low capacitance. Very, very good, or used very regularly in the radio industry. But we also have another type of capacitor that we had seen before, the electrolytic capacitor. Now, the thing about electrolytic capacitor is that it's polarized. One value is positive and the other value is negative, or you have plus and minus on the two legs. Notice in the ceramic capacitor, we did not say that. It really doesn't matter for ceramic capacitor how you put it into the circuit. You could put it in straight, you could put it in reverse, it doesn't matter. There's no positive or minus in the ceramic capacitors. But the electrolytic capacitors, guess what? Yes, you have polarity. One is positive, one is negative. So we say they are polarized electrolytic capacitors. And notice the symbol is slightly different as well, right? So they are very similar to the ceramic capacitor type symbol, but because one is positive, one is minus, we have a slight adjustment. So just bear that in mind. The polarity is also very important, and we have to be careful when we are making up circuits, repairing circuits, that we do not cause reverse polarity. We do not put them in the wrong way. Just like a car battery. If you put your battery in wrong, you put the positive to the negative and the negative to the positive, you can cause real problems. But in the case of a capacitor, what could happen? You can cause the capacitor to short circuit if you put the positive to the minus and the minus to the positive in the circuit. You can destroy the dielectric layer. Remember, we saw what that dielectric layer was. It was between the two plates, kind of the peanut butter or the vegetable spread, right? You could destroy that. You could evaporate it. And you can cause the capacitor to overheat and explode, and therefore you can cause a fire. So therefore, we have to be mindful that we don't do this. But the good thing about electrolytic capacitors, remember we said the ceramic capacitors, low capacity. The electrolytic capacitors have high capacity, right? You can get very large values. Again, last class we talked about the people who have hard pong in their vehicles. When you look inside of their vehicle, you see a big capacitor, high capacitance, all right, for the given size and volume, all right? So notice that there's an error here. It said can, it shouldn't be cannot, it should be can be used where high capacitance is needed. So again, typo there. We'll correct the slides for the next class or when we issue the slides. So it can be used where high capacitance is needed. So it's now 9:02. We will take a short break. Please take a stretch, maybe a bathroom break, get some water, and we'll come back in about 2 minutes' time to continue with our theory. Okay, everyone, welcome back. So we move now to another type of component that we saw already. We have seen it a couple of times, and that is a component known as the inductor. And remember, an inductor looks like a coil of wire, and this is the symbol for inductor. And remember, we also said when we were using the water analogy that an inductor will also store a charge as well. So in the water circuit, it's like our pressure tank also, it stores a charge. But just like resistors and capacitors, they have different types of inductors. You have the plain old inductor that is air wound, you know, it's just wrapped around, it's coiled. And then you can put material inside of the core of the inductor, and you can wrap it around in a circle, and you know, you have different types of inductors, and we are just illustrating a couple of them here, but we will deal with one of these, which is the toroidal type of inductor. in a bit of detail. So, what is the toroidal ferrite coinductor? Sounds like a very long name, complicated and so on. And therefore, we do have an abbreviation for it in amateur radio. It's called the toroid. But it's really the toroidal ferrite core inductor. So we have a couple things on the screen here. First of all, the symbol for the toroid or ferrite core inductor is this one that's highlighted in red. So I just decided to show what, the different types of inductors with iron core, variable core, air core, what they look like, so you can have an idea of a comparison. But we are really talking right now about the ferrite core inductor, not the air core, not the iron core, not the others, but a ferrite core, and this is the symbol here for it. And on the right-hand side is a visual or a picture. We like to make it real so we can see what something looks like when we're talking about it. This is what an actual toroid looks like, or a toroidal ferrite core inductor. Nothing more than a coil of wire around this object here that's called a toroid. That's the shape, toroidal shape. And we take the wire and wrap it all around and come out. Yes? So some of us may be familiar with that sort of wrapping, right? So it's a toroid. Now, the thing about it by itself, the air core inductor, which is just the coil of wire, has inductance. But when you wrap it around a toroid like this, a ferrite core toroid or any other type of material, metallic like this, what you do is you increase the value of the inductance significantly. So we say here that you get a large value of the inductance when you put it around a toroid like this. The magnetic properties of the core may be optimized for a specific frequency range. Remember, we are using these things in radio circuits. So you may have a radio circuit for a particular part of the spectrum that you want to use it for, and therefore you optimize it for that value. Notice that it's telling us that most of the magnetic field is contained in the core of the toroid. So again, these are points that you will find in the exam, and that's why we have put them here. And these are specific to toroids, or the toroidal ferrite core inductor. So look at how it's constructed. A coil of wire around a toroidal ferrite core. And ferrite, as we'll come to very shortly in the next slide, is really the material that this thing is made from, right? That you're wrapping the wire around. So we'll come to a slide shortly that shows you what ferrite is and what it looks like on its own. But this is what a toroid or a toroidal ferrite core inductor looks like. All right, so we come to the ferrite material itself. So we note that there are different types of ferrite material. So if we look on the screen here, we will see, you have some ferrite cores here, and they may be made from different materials, different composition. And we say here that there can be a different composition or mix of material used in making the ferrite cores. Sometimes think of it as, a mason is mixing concrete. He may be paving the yard, so you'll have a different kind of mix of concrete. As opposed to, let's say, that same mason will be plastering your wall, right? So you'll have a different mix ratio, different amount of water to cement. He may put sand, he may put gravel, different types of aggregate he may put into it for you, or binders and so on. So it really depends on what the concrete is going to be used for. He'll mix it. Same thing with the ferrite material, depending on what you're going to use it for, what frequency range you're going to use it, the manufacturer will use a different proportion of different types of material in making the ferrite cores. So that's the point that they make here. You have a different composition or mix. All right. How the ferrite material is made will affect the performance in a radio frequency circuit. So when you're selecting a ferrite core, you will need to specify things like the value, the type of material, what is the cutoff frequency, and some other properties that we'll come to shortly about the ferrite cores. All right. So what is the practical use of this thing called the ferrite core or the toroidal core? What do we use it for? So if we were to look on our diagram, we will see that we have a radio, a transceiver, and then we will see on the other end we have an antenna. So we will introduce, notice inside of the box is open for you to see the inside. You will notice that you have coaxial cable that is wrapped around a toroid, several turns, and it comes out and goes. But why do we do that? What's the purpose of introducing? Why do hams use ferrite cores or ferrite beads, as it's sometimes called? Well, the reason is that when you do this, you add inductance to the circuit here. And when you add inductance, the reason you're adding it is to reduce or eliminate radio frequency currents that may cause RF feedback, which can cause equipment to malfunction. When you transmit, this is your radio here, and you're transmitting from this radio, you want all of your signal to go to the antenna. You don't want it to come back in here into your shack. So sometimes you will hear hams refer to this as an RF choke. They may call it a balun. You may even hear some hams call it an ugly balun, because sometimes when you construct it, it doesn't look like the best, and it's a big thing. So people say, hey, that's an ugly balun, just a term that they use. So those are some of the terms you'll hear amateur radio operators use when they say, hey, I've got a choke or an RF choke in my feed line, and they'll tell you I'm trying to use it to prevent RF from the shack. That's what they say. But the theory behind it is that it's reducing or eliminating the RF currents, which may feed back into your shack and cause your equipment to malfunction. How does it work? It works by creating an impedance to the current path. So that is why you have to also select the proper ferrite core to match the frequency that you're using. Also, the number of turns that you turn around the ferrite core is also important. So let's go into some tech on inductors and the concept of self-resonance. So first of all, no electronic component is perfect. So a resistor, for example, does not only have resistance. A capacitor may not only have capacitance. An inductor may not only have inductance. An inductor, believe it or not, may have some capacitance. Even though it's an inductor, yes, because a lot of these things are not perfect, all right? So we need to bear that in mind. So that's the first point that we are making here. Inductors are not perfect, but many components are not perfect, all right? So just bear that in mind. Kind of like us humans. All right, in addition to inductance, inductors also have parasitic capacitance that may be taken into account or must be taken into account. So this word of parasitic, you could think of it as stray capacitance or extra capacitance or some capacitance, right? But the technical term we use is parasitic capacitance. So if you want to sound, technical, you say, well, the inductor may have some parasitic capacitance. So that extra capacitance or level of capacitance could be a problem for you in your circuit. Imagine you want to put an inductor into your circuit to tune a circuit. But wait a minute. That inductor has capacitance. It's like, whoa, all right, that could be a problem for you. So you need to bear in mind that imperfection with the components. We also need to bear in mind that the frequency at which that parasitic capacitance of the inductor resonates with the ideal inductance of the inductor is called the self-resonant frequency. So it's SRF. We put the formula up, not that you need to learn the formula, but we have been putting formulas throughout our course. So it's useful for you to see what the SRF formula looks like. It's 1 over 2 pi root of LC. What is L? You remember that L is inductance and C is capacitance. So that is what the self-resonant frequency is. So we just need to know that that SRF or the self-resonant frequency is the frequency at which the parasitic capacitance of the inductor resonates or is synchronized or matches the ideal inductance of the inductor, and that is called the SRF. We have a little diagram to show where that occurs because that is an important factor in the inductors generally, and certainly the toroidal cores or the ferrite cores that you use. You want to know what is that SRF. Why do we want to know where the SRF is for our inductor or ferrite core? First of all, let's just take a note here that at this point of the SRF, the impedance becomes very high, so it appears as an open circuit, all right? So just take a note of that. But why do we need to know the SRF, or the self-resonant frequency. And remember, the self-resonant frequency takes into account the inductance and the capacitance. It is because when an inductor is operated above the SRF, above the self-resonant frequency, it becomes capacitive. So that is why the SRF is important. Once we know what that is, we need to make sure we operate that inductor below the SRF. If we operate it above, it's really no longer operating as an inductor as such. It is operating with high capacitance, and that may not be what is desired. In other words, it only acts as an inductor up to the SRF. After that, it acts as a capacitor. So think of it going all the way up to the SRF value, it is an inductor. After that, it starts to behave less like an inductor or not like an inductor and as a capacitor. So that is why as hams, we need to be familiar with the SRF, self-resonant frequency concept of inductors. Let's now move to another component that we touched during our technician class, the component that's known as a diode. And remember, throughout our technician class, to use analogies and to aid in the understanding of the electric and electronic theory, we use something that all of us are familiar with, water circuit. And we said that a diode was like a check valve in a water circuit. You know, if you have a water tank and you have the water being fed from the street, you know, your water authority in Trinidad and Tobago, we call that authority WASA. So when WASA has a pipe coming from the street to your water tank and it's filling your water tank, if WASA cuts the water to your water tank, you don't want that water in your water tank to drain back out and go back into the street or into the pipes on the street, right? So what you use is something called a check valve. That check valve stops the water from reversing or from going backward or going back into the pipeline of the supplier. You want to be fed the water, but you don't want it to be fed in the opposite direction. That is called a check valve. Well, in electronics, the equivalent of a check valve is a diode. Now, a diode is a very versatile item, right? But let's look on the screen to see here. We saw in the technician class, this was the symbol for the diode, very nice and cool, shows that the current will flow in only one direction. We showed what a basic diode will look like. But guess what? Just like inductors, just like capacitors, just like resistors as before, we have different types. Just like we have different mangoes, different cherries, you know, we have different diodes. Look at how many types we have, all right? So we have Zener diodes, we have signal diodes, we have all sorts of different diodes that exist, right? Pin diodes. So there you have it. And similar to the different types of diodes we have different symbols. Now we have shown this just for your awareness and comparison, not that you need to learn all of these. We will go through what you need to learn, but just for your comparison and awareness to see that electronics, very exciting field, so many different types of devices, so many things for us to learn, that it's very exciting. So it's just for your information. Let's go straight into what we need to know. So we need to know about the uses of diodes. What do we use diodes for? So we use diodes because they are very versatile to rectify alternating current voltages. We use it to regulate DC voltages. We use it to switch radio frequency voltages, and we also use it to detect or demodulate radio signals. And I've just put up the circuits that show how that works if anyone wants to look at it. We wouldn't spend a lot of time because you really don't need to know this for your exam. But as we said, you know, we like to touch the theory and give students a little something extra. So here are some circuits that matches each of these. So for example, rectification. We have an AC voltage. We pass it through a diode and then we get pulsing DC. So that is what we mean by rectify. Of course, those who are already familiar with electronics will say, but wait a minute, we are only seeing half of the cycle because this is a basic diode rectifier. But if we use a bridge rectifier, guess what? We will get the pulsing on both halves of the cycle, all right? So those who are familiar a little bit with more of the advanced electronics, that will be true. But notice rectification of the AC sinusoidal wave into the pulsing positive part of the wave. That is what rectification means from an AC voltage to a DC voltage. Regulation. Regulation is clipping and steadying, all right, maintaining a steady voltage. So the diode here, in which case is a Zener diode, it will keep the voltage below a certain, it will clip it and clamp it. If it goes above, it will clamp it and shunt it, and therefore it stays steady at no more than this value. And that's why we say it maintains a steady DC value, not exceeding this particular value. It clips or it clamps. It also switches RF voltages or radio frequency voltages. And we have a little circuit here that shows that you're using these diodes here to switch. For example, maybe you're having a crossband radio that does VHF and UHF, and you need to switch from one circuit to the next. You will use diodes to do that switching, for example. And of course, to demodulate radio signals, you have the radio signal coming in here with the carrier wave and the applied signal, and you pass it through the diode and the rest of the circuit, and then you have the output. So you're demodulating from that. All right. So these are some of the uses. You don't really need to memorize any of this, but this is just to show you how versatile diodes are, and these are actually what they're used in real world in electronic circuits. So we need to know this slide for exams. For diodes, there is a specification that we need to be aware of that's called the junction threshold voltage. All right, so that's a key specification for diodes, junction threshold voltage. And we need to know that there are two different types of diodes that we will encounter for our purposes. And it's really based on the material or the substance that they are made from. You have silicon diodes and you have germanium diodes, okay? And we want to make sure that we are aware that it is silicon diodes, because sometimes you'll hear people say silicone, which is not quite correct. It's silicon, that's the name of the element, silicon. So it's silicon diodes and germanium diodes. And we need to know that silicon diodes will have a different junction threshold voltage from the germanium diodes. So if we were to read here, it says that silicon diodes, which happen to be the most widely used type, most popular, they have a higher junction threshold voltage. And I have a note here that says that that junction threshold voltage, what it really is the minimum voltage you need to apply to the diode for it to conduct electricity. If you don't cross that value, it does not conduct electricity. The electrons will not flow. So you have to achieve at least that to be able to flow. You know, sometimes just like water pressure, the water pressure needs to be above a certain value to go up to, let's say, the second story of your house. If, you know, sometimes the water pressure is low and you're saying, but wait a minute, turn on the pump because you need a certain amount of pressure for it to go and flow properly. It's the same thing. You have a minimum voltage, and that's called the junction threshold voltage. All right. And because it's different, we need to learn what the different junction threshold voltages are for both silicon and germanium. So for silicon diodes, it's 0.7 volts or 0.7 volts. And for germanium, it's lower, which is 0.3 volts. And we have that in the graph here. You notice that as the voltage goes up to 0.3 volts, then the diode starts to conduct. Before that, notice it's not conducting any current at all, zero. And same thing for silicon. It doesn't conduct, it doesn't conduct, it doesn't conduct. And as soon as you get to about 0.7 volts, it starts to conduct. So this is just showing here that no current flows until you cross that junction threshold value. Now, some people will say, but how do I remember whether silicon was 0.7 or something else and germanium was 0.3? Well, first of all, when you add up both of them, you get 10. So it's just 0.7 and 0.3. Sorry, when you add them up, you get 1. So 0.7 and 0.3. And then you want to know, well, okay, how do I remember the germanium diode is 3? Well, a lowercase g, if you look at the G for germanium here, it kind of looks like a 3. You just take out a piece of the circle. So if you want something to remind you that germanium was 0.3, just look at G for germanium here in the lowercase and just take out the circle and it'll look like a 3 if you need something to help you remember it until you remember it, right? Sometimes we need these aids de memoire to know how to remember something. So silicon is 0.7 volts junction threshold voltage and germanium is 0.3. So we now come to transistors. Again, like we have seen for all the other components, there are many types of every component that we are dealing with. It's amateur radio. So therefore, we have to look at it And recognize that just like all the other components, we have different types of transistors, different cases, different connections, different technologies, and so on. So this here is a little plethora of the different types of transistors that exist. And we also have symbols to go with the different types of transistors, whether they are bipolar, field effect transistors, and so on and so on. And we'll come across that again in the next slide of the two types that we want to make sure that we are very familiar with. So again, we talked about transistors in the technician class. But here's what we need to know for the general class. We need to know that there are two categories of transistors. Now, transistors are very, very popular. They're very much utilized heavily in electronic circuits. And as an amateur radio operator, you may encounter them when you're doing repairs or you're building circuits and so on. So we need to know about the types of transistors. But there are two basic packages that transistors will come in. Either they will be as a single transistor by itself, or they will be part of an integrated circuit, sometimes what we call a chip. And inside of there, you could have millions of transistors inside of an integrated circuit. So those are the two basic types of packages that you will get transistors in. A single transistor, one transistor, or an integrated circuit. It's the same way that you could go, maybe you could go to the grocery and buy one egg, but then you could go and buy a tray of eggs. So think of the single transistor as one egg, and think of the integrated circuits as a tray of eggs, several eggs in one package. Now, there are two main types of transistors, or two categories that we need to be aware of. You have the bipolar junction transistor, or simply called the bipolar transistor, and this is the symbol below here. Again, we touched this on the technician class. We are basically repeating this from the technician class. And then we have the FET, or the field effect transistor. And the symbol here, you have drain source gate, and it's a different symbol for the field effect transistor. But those are the two different types of transistors, or the categories of transistors, broad categories that we need to be aware of, the two types. We are going now into a special type of field effect transistor, and this will be our last topic for today's theory. This type of field effect transistor, remember we said there are two types, bipolar transistor and field effect transistor. So this type of transistor, called the Mosfet, is a type of field effect transistor. And Mosfet stands for metal oxide semiconductor FET. So we abbreviate it as Mosfet. And on the right-hand side here, you have a P-junction type Mosfet, and this is what it may look like in a real terms. When you look at the component, this is what it may look like. But the important thing for us to know is that the Mosfet is a type of FET. The Mosfet is a type of field effect transistor. We need to know that. And we also need to know that what makes it a Mosfet is use of what we call the metal oxide layer that is used to insulate the semiconductor layers from one another. So that's why we have a diagram here showing how this thing is constructed. A little bit complicated it may appear, but we have it up here to show that there's this layer called the metal oxide insulator that insulates the semiconductor layers from one another. All right? So that is all we really need to do in all of this complicated diagram that we have here, that a MOSFET uses metal oxide layers. And that is actually why it's called a MOSFET, metal oxide semiconductor FET. And therefore, it stands to reason that we are using metal oxide layers. But what is it used for? It is used to insulate the semiconductor layers from one another. So think of it as like a washer or something that you would use to insulate one thing from touching the other. So it's an insulating layer between the various layers of the actual MOSFET device. That's all you really need to learn for the exam. And we show a diagram here that convinces us that, yes, there's really a layer inside of here called the metal oxide insulator layer. So that is it for our theory for today. Certainly, we'd like to encourage persons to continue reviewing the technician class material if you have not yet completed. Very important to help us with the foundational knowledge. Again, just to mention, email messages are sent to participants at least once a week. So if you're in the class and you're not getting an email, we don't have your correct email. Also, we have been sending weekly SMS text messages to persons as well. So if you are not, or you have not gotten any text messages, it's either we do not have your current mobile number, or you live in a country where SMS bulk messages are blocked. All right, so just WhatsApp me or send me an email if you're not getting those SMS messages, text messages, or the emails. Since the class has started, we have sent out at least one per week. And of course, around the world, but certainly in Trinidad and Tobago, our COVID-19 cases continue to increase. And of course, we have been having some very high death rates, very sad indeed. So we're asking all of you, please be safe out there. Again, just to remember, the month of May is REACT month. And also in Trinidad and Tobago, the month of May has also been declared by the government of Republic of Trinidad and Tobago as National Disaster Prevention and Preparedness Month. So look out for the activities that are coming and ongoing during this month. And just to advise, we do have a special event coming up towards the end of this month, a panel discussion that will be entitled The Role of Radio Communications Technologies in Disaster Prevention and Preparedness. So we will announce further in the upcoming classes for persons who are in attendance that would like to be part of that panel discussion and participate. So folks, our next session will be scheduled, God's willing, for next Friday, the 14th of May, 2021. Usual start time at 8:30 p.m. for approximately 1 hour. The time is now 9:33 p.m. And we'd like to say thank you for your kind attention. And please be safe out there. Do have the rest of a good night and a great weekend ahead. And take good care, everyone. Thanks a lot there, George. You as well, Desi. Thanks very much. Chevron, have a good night also. Paula, good night. Okay, Adesh, take good care. Bobby, good night too. You're certainly welcome, Adrian. Gary, do have yourself a good night too, man. Take good care. Okay, Ramzan, yes, you be safe as well. Sylvester, good night too. Yes, indeed. Sorry about that. Made an error. You're quite correct, Yasmin. The next class is actually on the 21st. My apologies for the error. It's the 21st of May is the next class. Today is the 14th, right? So 21st will be our next class. Good spot there, Yasmin. We do have a couple of errors on this slide. We'll correct them before we distribute. Certainly, George. Yes, indeed. Cert training coming up. Natasha, have a good night as well. Okay, Nicole, take good care. Good night. All right, Ian, no problem at all, man. You're welcome. Kevin, take it easy. Yes, correct. I made an error. It's the 21st. All right, so thanks for the correction. Anthony, have a good night as well, man. Arvind, have a good night too. Okay, Charlene, you too. Good night. Take good care. And Jessica, certainly, you're certainly welcome. And you also be safe. Take good care, everyone. Okay, Eustace, you're welcome and have a good night as well. Jerome, good night, man. Take good care. All right, Mark, have a good night as well. Be safe.